we're going to look at octane number. So our learning intentions are to explain octane number and its link to autoignition, and to discuss ways of improving octane number, including isomerization, dehydrocyclization, adding oxygenates, and catalytic cracking. So let's begin by looking at octane number, and we'll start with a definition. So octane number is the measure of the tendency of a fuel to resist autoignition, and this definition comes up quite often, and it needs to be known word for word. So in that definition we meet autoignition, so it's important to define that as well. And autoignition can often be called engine knocking, and it's the premature ignition of the petrol-air mixture before normal ignition of the mixture by a spark takes place. Now, petrol mixtures that are rich in straight-chain alkanes, such as hexane, can often ignite too quickly, and this can cause autoignition. But petrol mixtures that are rich in branch-chained alkanes can burn smoothly and efficiently. Now, it's a good question to wonder how the octane number of a fuel is obtained. So the octane number of fuel is obtained by comparing the combustion of the fuel with a mixture of two reference hydrocarbons, heptane and isooctane. So heptane has an octane number of 0, and isooctane has a octane number of 100, and these are the two structures here, and you need to know their names and how to draw them and their octane number. So there's different factors that can affect your octane number. So the first is the length of the chain, the length of your carbon chain. So the shorter the carbon chain, the higher the octane number. The second factor is branching. So the more branched chains, or the more substituents that there is, the higher the octane number. And then cyclic compounds, they have higher octane numbers than straight compounds. So what we're going to do now is we're going to look in the next few slides at how we can shorten the length of our chain and create more branching. Back in time, lead was actually used to reduce knocking or reduce autoignition, as petrol didn't have components with high octane numbers. However, awareness of potential health hazards caused by the poisonous addition of lead through pollution meant that they needed to come up with other ways to increase octane number. And lead was also causing poison of catalytic converters in cars, which meant there was more harmful gases being emitted to the environment. So the four main ways now in current time that we use to increase octane number is isomerization, catalytic cracking, dehydrocyclization, and adding oxygenates. And we're going to look at each of these individually and give some examples. So the first one is isomerization, and this involves changing straight chain alkanes into their isomers. And this is done when alkanes are heated in the presence of a catalyst, and this causes the chain to break, and these chain fragments then join together to give branched alkanes, increasing the octane number. And if you look back at when we were doing alkanes, you will see examples of isomerization in butane and pentane. So here I'm going to show you an example of pentane just to remind you. And in factories, pentane, which is found in the petrol fraction, undergoes isomerization, where we have this CH3 here on the end swapping with this hydrogen here, creating isopentane, or as we would commonly know it as 2-methyl propane. Now you'll see here the arrows that we have here, this is an equilibrium arrow. And the reason the equilibrium arrow was there is isomerization reactions do not always go to completion. Instead, a state of equilibrium is reached, and the mixture formed consists of straight-chained hydrocarbons and branched isomers. So in oil refinery, the straight-chained and branched isomers are separated from each other, and the straight-chained isomers or straight-chained alkanes are are recycled over a suitable catalyst to convert them into branched isomers, and this increases the octane number of the petrol as a result. The second way to increase octane number is by a process called catalytic cracking, and there's a large demand for petrol, so often the surplus heavier fractions from fractional distillation are used to create petrol, but they have to undergo catalytic cracking first. So this is our definition for catalytic cracking. It's the breaking down of long-chained hydrocarbons into shorter ones by the use of heat, which would be approximately 500 degrees, and a catalyst, which is often silicon and ammonia. So when these long-chained hydrocarbons that are in the heavier bottom fractions of your fractional distillation column, when they undergo catalytic cracking, they're cracked into shorter chains, which tend to be highly branched, and as a result have a higher octane number. So a common example of catalytic cracking would be splitting an alkane into a branched alkane and an alkene, and that's very common. If you're given a equation and asked, is this an example of catalytic cracking, look to see if you form a branched alkane and an alkene. If you do, more than likely this is catalytic cracking. So if you split a saturated alkane, one of the products must be unsaturated. So here's an example of catalytic cracking. So as you can see, I have a C12H26 compound, and it's cracked down the middle here. And if we look at this left-hand side first, we can see 1, 2, 3, 4, 5, 6, 7 carbons. And if we look, we can see 1, 2, 3, 4, 5 in the product, but the other 2 carbons are gone on as substituents. So here we've cracked and we have isomerized to form a branched alkane called 2,4-dimethylpentane. And if we look at the right hand side, we can see 1, 2, 3, 4, 5, but in our longest chain we can only see 1, 2, 3, 4. So again, this has formed an alkene, as you would expect, because this bond has broken here, so it must form here instead. But also this CH3 that's on the end has been swapped with the hydrogen that is here to give isomerization to increase your octane number further. And as I've said already, in catalytic cracking, the alkenes that are produced are extremely important for the petrochemical industry. Another way to increase octane number is dehydrocyclization, and this involves changing the shape of your hydrocarbon molecules. So cyclization is the use of catalysts or it could also be a cycloalkane going to an aromatic compound. So here's an example where we start with hexane that has an octane number of 25. If it undergoes dehydrocyclization, it can go to cyclohexane, which is an octane number of 83, but this cyclohexane could also undergo dehydrocyclization to form benzene, which has an octane number of 106. And you'll see each time dehydro means that you're losing the hydrogens and forming a ring. The last thing to do then could be to add oxygenates, and oxygenates is the name used by petroleum chemists to refer to any fuel containing oxygen in its molecules. So octane number is increased using the oxygenates, and they contain oxygen, as it says in the name. Oxygenates can cause less pollution by reducing the level of carbon dioxide in exhaust fumes, as it causes the fuels to burn more efficiently. And examples of oxygen-containing compounds are methanol, ethanol, or MTBE, which is methyl tertiary butyl ether. So that's it for this video. Have a read over the learning intentions to check you understand everything we've gone through.